people coming. Well, we'll start now. The introduction will take 2-3 minutes, so some people will have time to join us to start. So just firstly, thank you for joining this webinar, the last one of the year. So that's, I mean, for us, that's a really good opportunity just to bring you an overview of what has been done the last few years, or the last few months, and basically, specifically, how we can decrease energy consumption during a thermal desorption, which is the main cost driver, one of them at least, during a thermal desorption. So that's a good opportunity just to explain you basically where we are coming from and basically where we are going. I will be the host of this webinar. So I'm Aurélien, and I'm working department of the business development and engineering. I joined Amherst Technologies 9 years ago. Initially, I'm a chemist. But I'm not so the most important guy during this webinar. Our guest of honor will be Jean. Jean joined us almost 6 years ago. That's an engineer, and when he joined us, he was a project engineer, and he had the opportunity to work as a project manager also, and then he jumped to the accounting part of the project, and now we are working together on the business development and engineering departments. Just to give you, before starting this webinar, just to give you some practical information, this webinar will last between 20 and 40 minutes, and then we will do a Q&A sessions. The duration will depend, of course, on the different questions you might have. At the end of this webinar, we will send you a certificate of attendance of this webinar. And no worries if you have any issue with the connection or didn't have the opportunity, we will download this webinar on our YouTube channel. Enjoy just this webinar. That will be the last one of the year, and it will give you a quick overview of what was different improvement that has happened the last few years, few months. So Jean, I'll let you the floor and
Yep.
Talk to you later.
Yep. Thank you, Aurélien, for this nice introduction. So hello everybody, thank you for your participation. Aurélien already told us what will be the subject of this webinar, but I will tell you again. So this webinar will be about the decrease of the energy consumptions in thermal desorptions. So first of all, I will make a very quick company overview. So Amherst Technologies is a Belgian-based company with its headquarters in Brussels, and we provide remediation technologies all over the world since more than 25 years now. In order to be standalone, we have our own smart burners factory facility. And we also invested in our lab and research and development facility to develop new products and technologies. And I will talk specifically about those new products and technologies that we developed over the past few years. Here are some companies that already trusted us. So you might recognize like Exxon, Lingeneld, Evonik, or Séché, for example. We do the operation worldwide with a local partner. So here you can see a map of the sites where we already remediated soils. So we basically do most of our business in Europe here, but we also do some business in United States or the whole continent of America, or even in China. We have different kind of treatment, but I will talk about that later. So first, I will talk about the energy consumption. So this is know that you know a bit more about who we are. Let me develop what is our co-remediation technology. So I will tell you a bit more about what is the technology, and then I will tell you why energy consumption is a big field to invest on to try to reduce it. So first of all, as you might know, we are specialized in thermal desorption. So thermal desorption is a physical chemical technique that is used to vaporize the pollutants in the soil through heating the soil to the vaporized temperature of the pollutants. So how we do that? So basically, we create a flame. So this flame is generated in the burner, and the flame is conducted through two coaxial pipes into the ground, leading to an increase of the soil temperature by conduction. So here you can see that the flame is going here, and then it will hit the soil by conductions. So once the soil gets to the vaporization temperature of the organic pollutants that we want to remediate, the pollutants get vaporized. But then what happens to so we can either do the remediations vertically, so on site with in situ thermal desorptions, but we also can treat horizontally with ex situ thermal desorption. So it means we bring the soil to another site, and then or another part of the site, and we build pile and we treat the soil this way. And we also can do ISTD horizontally or oblique. So now that we vaporize the pollutants, we need to treat the pollutants. So either we will use a reburn, so it consists in injecting the polluted pollutants, the polluted vapors into the heating tube to get thermal oxidations. It will also decrease the total fuel consumptions. So if we cannot do reburn because the pollutants will produce more dangerous compounds, we will need to use a vapor treatment unit that will be placed ad hoc. And it will be used to condensate and then treat the vapor. So basically we can treat the vapor through thermal oxidizer or activated carbons. We also can use thermoreact, which is an in situ technology used to neutralize acidic compounds. So now that you understood a bit more about how thermal desorption works, you understood that we need energy to fuel the technology. Like, it doesn't run by itself, unfortunately. So in this slide, let's do a little game. What do you think are the items that requires energy when applying thermal desorptions? So I will do a kind of a life cycle assessment of thermal desorptions, but of course I won't get that precise because it will take so much time to do that. But first of all, we need energy to fuel the conductive heating. We need fuel to bring energy to the soil. Then we also need energy to fuel the equipments that are used to run thermal desorptions. And then we also need some energy to fuel the engine, like the drilling machine, the excavators. We will also need energy for the material transportations and the people transportations. But on this webinar, I will only talk about how to reduce the energy consumption to fuel TCH and the energy the energy that we can reduce to run all the equipments. So first of all, what kind of energies we can use to fuel the equipments. To fuel the equipments, we require electricity. So as an example, for standard ex-situ thermal desorptions of 2,000 cubic meters, we'll need about 50 kilowatts of power to run all the fans, the blowers, and we will also need some energy to treat the vapors. But what is the most consuming is not to run the equipment, but the energy to fuel the TCH. So we will need energy to bring calories to the soil. So we usually do it by burning hydrocarbons compounds. So it means hydrogen plus carbon compounds through our smart burners. We will adapt the fuel burner to the place where we have to treat the soil. So as an example, we can use natural gas if natural gas connection is possible. We also can use diesel, for example, if it's in the desert and there is plenty of diesel. We also can use propane. And we also can use, for example, like cocoa oil if we are on an island full of coconuts. I don't know, like we already did that. So yeah, and on the places where we cannot place hydrocarbonized fuel, we will need electricity. So we will do it through resistances, but this resistances cost a lot at the moment because of the crisis and everything. So we basically prefer to treat through natural gas, diesel, or propane. So now that you know a bit more about the fuel, let's talk about the repartitions in thermal desorption cost. So here you can see a camembert scheme with the ratio for each category. So you see that the first category will be the people. So like indeed, thermal disruption requires people for building, supervising the installations, and everything and so on. And it's followed by the energy cost and the fuel cost, like it's about 30% of the total price. As you can see here, the electricity to run the equipment, it's not so much because of the low cost of the energy, and because thermal disruption doesn't require so much energy if we don't use resistances. The other categories represent less costs. So now you understand that there is a high impact of the energy consumptions in the cost. So when we talk about energy, we need to talk about the global efficiency of the system. So Hammer's technologies used to obtain like a global thermal efficiency of about 30 to 50% in the past years. But now today, like since 5 years, we are a bit happy, to obtain a thermal efficiency of about 60 to 80%, which is really great. And that is leading to a huge decrease of the energy consumptions. So now the question is how we did to decrease to increase the treatment efficiency and to decrease the energy consumption. So that's the core of this webinar. So now I will talk about all the strategies that we use to decrease this energy consumption. Sorry. So as I already explained, we require energy in thermal disruptions, but let's get in details in the process. On which field can we work to decrease this need of energy? What are the factors of influences? So first of all, I will talk a bit about what we can do in detail engineering to decrease the global thermal efficiency and the energy consumption. Then we also can work on the burner efficiency to reduce, for example, the energy losses. And there is another factor that is the treatment times, because if we manage to decrease the energy consumption through detail engineering and burner efficiency, if the treatment time is still like very, very long and is not reduced, then we will still use a lot of energy. So we really need to work on the treatment time. So let's talk about the detail engineering. To get better into detail engineering, we need to optimize our design of ESTD or ISTD. We learn about using the powerful software that is called Fluent. So this software is used by the NASA, I think, and it is used to modelize the fluid mechanics. So it's very complicated software, but we worked on it using the field experience, and we could enter the main constraints of thermal disruptions, such as groundwater, humidity of the soil, interdistance of the burners, etc., etc. So thanks to that, we now can modelize the heating of a site before going on site. So this will help, to optimize the spatial distributions and also to better estimations of the energy consumption. So before going on site, you will know like exactly what will be the energy consumptions if there is no other problems. So here you can see, for example, for the same site, two kind of design that we did. So after 40, so this is the treatment zone in white. We first decided to place each burner at 3.5 meters of interdistance of each. And with those simulations, we could see that on some parts of this design, we could not reach the targeted temperatures after the treatment time that we wanted. So we decided to optimize the interdistance. So the interdistance was still 3.5, but we decided to add 15 burners like in the borders to be able to reach the targeted temperatures after 40 days. If we did not do that, then after 40 days, we will still be in these situations, and then we will need a lot of time to reach the target temperature in this zone, for example. Then we also developed our core technology, that is the development of a burner. So 5 years ago, we used to use very old burners. They were very easy to use, but they were very old, and they were consuming like 2 kilowatts per meter. And now we developed a remote flame burner. So the remote flame burner led to a decrease of the energy consumption of about 20%. So this gain was because the flame is not created outside of the soil, but now it's created inside of the soil. So we don't have the energy losses with the cold air and everything. So for example, in a project in Corsica, we used a remote flame burner. For the second batch, and for the first batch, we did not use it. And we went for the first batch, we were at 200 kilowatt hour per ton. And after the second batch, we were at 100 kWh per ton. So that is a 25% of gain. So that's really much. But in general, it will be a 20%. Then we also developed the VX, that is the new technology of burner. So the principle is to use the residual energy for the combustion. So instead of bringing cold air in the burner for a good combustions, we bring the hot air that is coming from the already done combustions. So that will help us to have a better efficiency. On the VX, we have a 30% decrease of the energy consumption. So that's a lot. So thanks to those improvements of burners, we could pass from 1.5 to 2 kilowatts per meter injected in the tube. So in this 2 kilowatt per meter, we had 1 kilowatt per meter to really hit the soil, and we had 1 kilowatt per meter that was completely lost in the air. And so nowadays we are about 1.4 to 1.6 kilowatt per meter. And we wish to get to 1.1 to 1.3 kilowatt per meter. We will not be able to reach 1 kilowatt per meter because this is the really maximum. So we will always have some losses and everything, but we wish to reduce it at the maximum. So now I will talk about the way to decrease the treatment time. First of all, there is the on-site monitoring. So we need to be sure that the heat is distributed well in the heating tube, because, for example, if on a heating tube you have like at the beginning of the heating tube, we have 400 degrees, and at the end of the heating tube, you have 100 degrees. Then the soil won't be heated the same way, like at the beginning of the tube and at the end. So we cannot stop the burner because there is one side that is cold and one side that is not cold. So in order to do that, we basically place thermocouples. So here you can see thermocouples through the heating tube. So for example, here at 3 meters in the middle of the heating tube and at the end. And if we don't have a good distribution, we need to regulate the airflow and the gas injection. Here you can see a thermography, so a temperature map inside a pile, for example. And in this case, we had a very bad, so it was back in the days, we had bad distributions. So you could see that at the beginning of the heating tube, we had very hot temperature, and at the end, very low. So the soil was at a very low temperature. So we had to wait a lot until this place could get to the targeted temperature. So we lost a lot of gas for that. We also analyzed the soil temperature at the cold point. So this means at some point that are the farthest from the heating tube. So thanks to those data, sorry, I will drink a bit. So thanks to those data, we can draw thermographies. So here you can see a little graph with all the temperatures. So this is the temperature and this is the days. So here you can see the temperature is rising. The targeted temperatures was 90 degrees on the site. And we can build thermographies to have an overview of the temperature evolution. So this helps us to adapt the heating settings to the temperature evolution. So for example, if on this part of the pile we are very warm and on this part we are cold, we can inject more gas on this part, for example. Then I also wanted to talk about the heating modelization that I talked previously. So thanks to this heating modelizations, we could obtain theoretical heating curves. Then when we are on field, we can compare these curves to the field. So here you can see in yellow that is the heating, the theoretical heating, and here in red, in green, sorry, this is the on-site heating evolution. So on this graph, you can see that they are very close, but on some sites we see that the temperature evolution is not the same. So that means there is a problem. So this helps us to have a better reactivity on non-visible issues, so on issues that we did not see yet. We also can monitor the pollutant concentrations into the extracted gas. That will help us to draw a mass balance estimates. So we'll basically, like for example, here place our equipments and measure the combustion gas here. So yeah, so this helps us to draw a mass balance, so we know what is the quantity of pollutants that have already been removed from the pile and what is still remaining. So as an example, this machine, it will measure the CO. So when you have a site contaminated with hydrocarbons, for example, CO is a big marker of hydrocarbons concentrations. So when you don't have CO anymore, when it's reducing, it means that you get to the optimization and that there is not so much more contaminants into the soil. So this also helps us to know when we need to stop the burners. So when all the factors that I explained previously are okay, we do some hot sampling. So it consists in the sampling of soil inside the pile while the treatment. This also help us to draw a remaining map of the pollution into the soil. So here, as you can see on this figure, so here are the spots where we did some hot sampling. So here, so it's basically one at the back and one in the front on a lot of parts of the site. So then we know which part we can shut down and which part we need to increase the gas injection, for example. So here you can see that, for example, here the concentration were okay, so we met the objective. So we could stop the burner, shut down the burners without disturbing the heating of the rest of the pile. So thanks to that, we can switch off some burners before the treatment time, the final treatment time. So this has a huge weight on the energy consumption. So, like for example, if you treat for 45 days, if you treat for 45 days or for 50 days, it will make a huge difference. So, for example, here on this part, we stopped after 30 days, and here on this part after 50 days. So that made a lot of gas decrease consumption. So now I will talk about the perspective. So we really think that in the future, thermal desorption should be the backbone of a sustainable remediations on heavily contaminated sites or hotspots or sites that cannot be remediated through other remediation technologies. So we think that the combinations of the remediation technique is the future, because it will also lead to a better global efficiency of the site remediations, because maybe the thermal disruption itself won't change, but if we add it to another type of remediations, then the global remediation of the sites, the global efficiency will be better. So I will give you some examples. So we could, for example, use thermal disruption with bio. So, for example, if we have a site where the groundwater is contaminated and also the soil, so we could heat the soil up to the target temperature and only heat the groundwater at 40 degrees, then it will enhance the bioremediations. That's a possibility. Or another possibility is, for example, on some sites, we called us to do thermal disruption on very heavily contaminated soil, and the other soil that were like less contaminated, they were treated through bio. So, and if bio couldn't reach the standard, then the soil was then placed in thermal disruption. So that's already a great great example. We also can use thermal disruption with chemical oxidations. So in the groundwater, or if we have residual contamination. So we used it in Italy after thermal disruption. So when the soil is at like 70 degrees, we inject, for example, persulfate, and then this will help to degrade the rest of the pollutant. And thermal disruption is great for that because it will like activate the persulfate. If the soil is warm, the persulfate will have a better efficiency. We also use thermal disruption with venting on two sites. So, for example, it was in Corsica or in England. It could be used for volatile pollution. So, which means that we don't really need to get to the really high targeted temperature, because next to thermal disruption there will be venting that will also catch the residual pollution. So by combining all those techniques, we really think that we can decrease the global efficiency of the remediations of any sites. In the meantime, Amherst Technology will also continue to develop product to reduce its own energy consumption. So it will be done by another type of burner that is called VX control. So the VX control it's the same as the VX that I explained before, but we can control everything by distance. Like it means that all the data of the burner are controllable with my computer. So it means if I am in Brussels, I will be able to control all the parameters of my burner that is in Tahiti. So that is great because we can, for example, decrease the gas injection if we see that there is not so much residual contamination. And we imagine that the VX control can also control much more parameters, but maybe we'll talk about that later in next year in another webinar. With all the data that the VX control will also manage and take, we really think that we want to input those data into AI, artificial intelligence, to understand better what's going on in thermal disruptions and what is going on in the soil. And we also think that we can create new inventions. I don't know I don't know what can be those inventions, but maybe we can think about like solar or thermal desorption, or yeah, that's why we still have a big research and development team to create new inventions and maybe to be like to have the best efficiency in the world remediations. So to conclude, so the treatment time plus a decrease of the treatment time plus a decrease of the treatment, an increase of the treatment efficiency, plus combination of technologies and some innovations, such as burners or better control, will lead to us to a better sustainability and a better, total decrease of the energy consumption for thermal desorption. Thank you for listening. I wish you a Merry Christmas because it's in 4 days, 4 or 5 days, depends if you where you are. But yeah, thank you for listening, and have good vacations if you have.
Thank you very much, Jean, for this very interesting and technical presentation. So I'm sure that because there were many information, a lot of information shared during this presentation, I really invite you to watch again the replay on our YouTube channel. So we still have a few minutes in front of us. So we have a few questions, Jean. Maybe I will start with, can you please just go back to the slide 24?
Of course, I can. 24, this one.
Yes, perfect.
Yeah.
Or maybe the last one, can you just, to previous one?
The previous
Yeah,
one.
we were talking, because the question is from Lars Van Passel. The question is like to monitor and to follow up the treatment. You are basically following the CO concentration, and the question of Lars is like, I assume that it should be CO2 and not CO to follow up the treatment. So I don't know if you can maybe elaborate and give more explanation about why we are following CO and not CO2.
We are, yes, of course. Thank you for the question, first of all. So CO2 is CO, sorry, is a marker of the good combustion or not good combustion. So if we have a lot of CO, it means that there is a lot of contaminants going into the flame. I'm talking about reburn for now. Like we are following CO for reburn, and so if we have a lot of CO, that means there are a lot of contaminants that are going into the flames and that are going to be combusted. That creates a lot of CO, and if we don't have a big charge of contaminants going into the flame on reburn, then we won't have so much CO anymore. So that's basically why we are monitoring CO. We do monitor CO because it's a marker of combustions, good combustions or bad combustions. If you want to add something, Aurelia?
Yeah, no, that's okay. And also for our information, it's like the CO concentration. Basically, we are talking here specifically about the heating tubes. But if you are following exactly the concentration of CO in the vapor tubes, what you will see, we will get a peak of CO during when we are desorbing a lot of contaminants into the soil. But this CO after has to be oxidized in CO2 before being released. But that's also a really good marker to know exactly if we are desorbing, if there is any more, no contaminant anymore into the soil.
Yeah, but it's working for hydrocarbons. But like for example, if you have chlorinated compounds and you need to have a vapor treatment unit, we will monitor the contaminants in the vapors in the treatment units. So we won't monitor CO in the treatment units.
Absolutely. Okay, another question. So to be clear, you don't release CO to the atmosphere. Yeah, to be really clear, we are respecting and we are meeting the standard at the stack, at the chimney. So you are producing CO, it's because of incomplete combustion, so that's why we are adjusting the burners. And coming from the vapors, every time we have CO, it has to go after to a specific vapor treatment unit. So yeah, to be clear, we don't release CO. Another question, which is the best fuel to use in terms of cost? It's quite a big question, so I don't know if you can just enlighten us.
I think it depends where you are and when we do the thermal desorption, because like for example, if you use propane or natural gas, the prices of those two compounds they changed a lot on the last few years. So nowadays, natural gas is less expensive than propane, but it used to be the contrary. And if I cannot really like tell you what is the cheapest the cheapest fuel, sorry, but like for example, if you are in a Arabic country, fuel might be like very cheaper than natural gas, so it will depend on some factors such as where you are and when you want to achieve this remediation.
Yeah. So just to summarize what you said, it's just like it's location depending. Um, so in few locations that it's really windy locations. So I mean, for this kind of space, maybe there is a process including the wind inside it. So I mean, it's site specific. Basically, what we are doing when we are arriving on the site is we are investigating further what are the different fuel costs. We still have 1 or 2 minutes in front of us, so I will jump to the last two questions. What is the temperature? So it's related to the beginning of your presentation. It was when you were explaining the principle of the technologies. And here is what's the temperature of the flame in the reburn process. So you have the hydrocarbons coming from the soil and reinjecting it to the burner bodies. What's the typical temperature inside it?
This the temperature of the flame, we can control it, so we can set it from 100 degrees to like 100 degrees. Basically, the standard when we are talking about hydrocarbons technologies,
So between
remediations.
1000 and 1600 degrees.
Yeah.
Okay. Okay. The last question, because here it's the last
100
minute.
to 1000 degrees. Yeah.
So what temperature does the evaporation start in the ground I mean, from which temperature you are starting to evaporate the contaminant into the soil?
That's a good question. You will start to evaporate the contaminants really before you get to the vaporization temperature of these compounds, because of the heat pressure of this compound. So, for example, if I talk about volatile compounds such as PCE, you will start to vaporize the TCE since like you are at 15 degrees, and then you will vaporize it more and more and more and more. And then once you get to like 100 degrees, you will vaporize everything. But the vaporization process really starts at normal temperature. Yeah.
Okay. So to keep the long story short, we are evaporating from scratch the contaminants. And the higher temperature, the higher the contaminants in the vapor we are collecting. All right. I feel maybe I have some few questions that will be answered during the mail, because here we just exceeded already from 1 minute to this webinar, which is not the purpose. So just Thank you once again, Jean, for this presentation and all these topics. That was really interesting. I really invite you to watch again this webinar on YouTube channel. And the last thing I can wish you, it's a Merry Christmas and Happy New Year. Have a good lunch, all of you.
Thank
Bye-bye.
you. Bye bye.